All right, good evening, everybody. Welcome to class. All right, so let's just jump straight into it. I was not sure I wanted to comment on Saturday's test before I went through it, but just a cursory review of what I saw was not very encouraging. Suffice it to say, I hope it will serve as a, for use of a better word, a wake-up call. I took note of many persons who, and I'm saying this for the benefit of the Wednesday group, since I didn't record, well, we didn't complete the recording for Wednesday, so they will have a chance to look over this. But I made note of the fact that quite a few persons who have not been attending classes made an attempt at with the test or the assessment, and the scores were reflective of their non-attendance. However, what was of even greater concern to me was that I looked at the assignment I gave you on superposition, which I uploaded the solution and asked you to review and mark your work. I then looked back last night and saw that only 5 persons did as was instructed. Those 5 persons, of course, will benefit from following the instructions that were given, as that will help to boost their test grade. But of greater concern is the fact that at least one of the questions, and I deliberately did it. One of the questions was repeated from that assignment. And looking back at what was done on Wednesday, it tells me that persons either do not understand the importance of completing work that I asked them to complete. But as I said, there are different objectives for my first test or my first assessment. The first objective is to give persons a wake-up call that, you know, there's a lot of work to be done, and maybe just how you approach doing your work will have to change. All right? So be that as it may, I trust we will not have the same challenges going forward. I will not address the whole matter of persons not being able to upload and that sort of thing. That's, you know, that's something I won't even seek to address right now, because some of the issues would have been identified had the work that I had given you previous been uploaded. You would have gotten a chance to practice uploading, know the little nuances that may exist. So students, while I teach you networks 1, I'm also a member of the senior management team of the faculty, and my responsibility is to ensure that those that we produce in terms of graduates are of the highest caliber. All right, so always bear that in mind. All right, I will not dwell any further on that assessment, but we will get straight into what we have scheduled for today. Last time I met you, I asked you to look over all the theorems that we had looked at, or the methods, the mesh analysis, the nodal, because we'll be applying them today. And so we just jump straight into that in terms of applying all those principles. So we want to start by looking at Thevenin's theorem. This is already written out in the notes, so you can just highlight the areas, the notes that I have already sent you, which you were asked to print. So, you know, you can just highlight the important parts. Okay, so Thevenin's theorem. It tells us that a two-terminal network which has resistances and voltage supplies and current supplies, that we can reduce that network of resistors and sources into a single voltage source in series with a single resistance. So that's Thevenin. You have a complex network with voltage sources, current sources, and of course resistances. We can reduce all of that into a simple network consisting of one voltage source and one resistor. The more important question is, how do we define that voltage and that resistance, all right? Which is on the next slide. So the EMF of that single source, all right, is the open circuit voltage or the open circuit EMF at the network terminals. So when I'm talking about Thevenin theorem and Thevenin equivalent, it must be at a particular point within the circuit. So it's the open circuit EMF at the network terminals, and the resistance in the Thevenin circuit is the resistance seen looking into the same pair of terminals, yes, when we replace all sources by their internal impedances, okay? So again, Thevenin says that we can reduce the network into a single voltage source in series with a single resistance, and then by definition, the voltage is the open circuit voltage seen at the terminals, and the resistance would be the resistance seen looking into the same pair of terminals, okay? So that's by far what we use in terms of explaining Thevenin. But to better understand it, we want to look at the application. How do we apply Thevenin's theorem in terms of circuit analysis? Now, the circuit we have on screen is one that we have analyzed using mesh analysis and nodal analysis. And I think we also used Kirchhoff's laws in analyzing this circuit. So what I'm going to do this evening is to redo the question, but this time we are going to apply Thevenin's theorem. And what we are interested in is the current through the 24 ohm resistor. So here's my resistor, all right? And we want the current that is flowing through it, okay? So you can look back at the solution that we had before. So when we do the Thevenin, you can compare and determine whether or not, you know, we have completed the solution correctly. All right, so based on the definitions that we just had, the first thing we want to do is to open circuit the point at which we want to find the Thevenin equivalent. So I'm going to redraw the circuit, and I'm going to remove the resistor for which I have an interest. So we remove the 24 ohm resistor. And what we want to find is what's the Thevenin equivalent looking into those terminals. All right. So we want to calculate the open circuit voltage, which is E Thevenin. Now, based on this circuit, based on the circuit with the open circuited terminals, given the remainder of the circuit, meaning the other resistors and the sources, that open circuit voltage, what would it be equivalent to? Anybody? Based on what we have here. What would be the voltage if I were to put a voltmeter across those open circuit terminals and measure that voltage? What would it be equal to?
The voltage across the parallel branch.
What do you mean by parallel?
The voltage across the 6 and the 35 volts. 6 ohm
Okay.
and 35 volts.
So it's a voltage across this branch, right? We can't say anything about parallel, right? And I don't want you to be making those sort of errors at this stage. Okay? Mr. Bogle?
Yes, sir.
Okay. So I'm gonna assume that you said parallel because it is vertical. I don't want that sort of error. We have to move on from that type of error. Yes, but you are correct, right? So we are looking at the voltage across this branch, yes, which consists of the 6 ohm resistor and the 35 volt source. Now, for this theorem, why I asked you to review the methods that we have already looked at is that in calculating E Thevenin, know that you are clear that you want the voltage across this branch, yes? You must now determine which method you would like to use. So there's no one method that you're going to apply in finding E Thevenin. You can determine that you want to use Kirchhoff's mesh, node. It's totally up to you. All right? And we make that point, that the method used to determine the voltage is based on which one you consider to be the easiest. Has nothing to do with the lecturer. It's what you are comfortable with. All right? Of course, we gave you all those methods and we looked at the different scenarios because with time, you will begin to appreciate that some methods are easier than others, depending on the structure of the circuit, okay? So we have already established that the open circuit voltage is the voltage across the terminals, circuit terminals being considered. And in this case, it is the one with the 6 ohm resistor and the 35 volt source. We have already established that, all right? So for my purpose, we're going to apply the node voltage method, okay? So we want to find V1. Now, based on what we discussed last week for nodal analysis, let's see now, Mr. Lawrence, and listen carefully to the question. Based on what we discussed in terms of the application using nodal analysis, the assignments we have here, would that be consistent, yes, with what we discussed last week? Based on the node voltage assignments, would that be consistent with what we had last week?
So could you repeat one more time? We're kind of breaking up on my end.
Okay, let's try again. Based on what we discussed last week, you hearing me clearly now?
Yes, sir. You're kind of better, sir.
I don't know what is happening. Based on what we had last week, based on the assignments, with
Yes,
what
sir.
I'm now showing on screen, would it be consistent with the rules that we specified last week? Just look at the assignments, and I want you to think of the approach we took in terms of the assignments. Would that be consistent with what I have on screen?
Yeah, I think so.
You think so? You're not sure?
I'm pretty sure, sir. Yes, sir.
Okay. What do you say about that, Mr. Farrell? Is it consistent with what we said last week?
Yes, sir. It looks so.
It looks so. Still not sure. Anybody?
Yes, sir.
Is it consistent with what we said last week in terms of the application? of nodal analysis?
Yes, sir.
Yes.
Would you,
No, the same thing, boys. No, the same thing, boys. All right. So what this is telling me again is that maybe you were zoning in a lot on the upcoming assessment. But this is not consistent with what we said last week, all right? Because what we said was that the principal nodes are nodes where we have current division. Remember that? You remember I was saying something like that?
Yes, I remember that.
So based on that, how many nodes would I have had for this circuit? How many principal nodes would I have had in this circuit? Pardon?
One, sir, including one, sir.
One. All right. Based on what we said last week, this would have been the only node that we would have considered. Yes? However, I'm now expanding it and say we can now use that point. Yeah? Because V1 in this instance would immediately give us the value across that branch. Are you with me? So I gave you the classic application. However, given what we now have in the circuit, we can break it down further and include the two principal nodes. All right? So from this, we have V1 at node 1. Right? That's our equation. I don't think I need to go through the equation anymore. All right, you should be good by now. So we're looking at the current going that way, looking at current going that way. The current's leaving that node. So we have V1 minus 35 over 6 and V1 minus 2 over 8. We simplify, and that's our first equation. Okay? And then for node 2, yes, we have 2 over 20, 2 minus 1 over 8, and 2 plus 25 over 2. We simplify, and that's our equation. And then, of course, we solve. And note, although once you plug this into your calculator, you're going to get the values of both V1 and V2. What we're interested in is V1, because what we want is the open circuit voltage. All right? So we simply extract from that what we're interested in. So V1 there would be the voltage at that point relative to the reference or to Earth. All right, so if I measure between that and Earth, I would get 16.667, which means that it would be the voltage seen across that open circuited terminals, what we call a port. All right, any questions?
Sir, could you repeat? I could hardly hear you.
Pardon?
I could hardly hear you, sir. Could you repeat, please?
I said a lot of things, Joe. Specifically, what are you unclear about?
The last part you were saying about the earthing, and then
I said V1 is the voltage at that point relative to Earth. So it will be the voltage across here. All right. The next step is that we now look at the resistance seen looking into the terminal. All right. So looking at the resistance looking into the terminals. So we redraw our circuit, we draw the network, and we are going to replace the sources by their internal impedance. All right. Okay, so looking into these terminals for the resistance, what's the resistance equation? What's RT? Looking into these terminals, what's RT?
14 plus bracket by
Pardon?
per
Go again?
14.
14.
Yeah.
Look carefully at the circuit.
So
Yes.
6, which is in parallel goes to the circuit, and 8, which is in series, goes to the circuit, 5 in parallel.
Thank you, Ms. Armstrong. That gives us 4 ohms. So the Thevenin equivalent would now be that open circuit voltage, which we described earlier, in series with that resistance seen looking into the terminals. All right, so now that I have the Thevenin equivalent, what I do is to simply reconnect the 24 ohm resistor and find the current flowing through it. In this instance, the current is 595.24 milliamps, which is what we would have calculated before, yeah? So you can confirm that using the methods that we had already used. So We find the Thevenin equivalent, so we find the open circuit voltage, we find the impedance looking into those terminals. That becomes our Thevenin equivalent. Then we reconnect the resistance to find the current. Anyone unsure of what we just did? In terms of the Thevenin principle, the principles regarding Thevenin.
Yes, sir. Can you explain it, please?
Yeah, Mr. Sir, I'm 100% sure.
About what? I'm not going to teach it over again. I'm asking you, tell me exactly what you're unclear on.
Sure. All right. Me not 100% sure upon the voltage part, sir. Or you get the what I call it, to explain myself right way. All right, sir. So after I broke up the circuit, sir, I you work out the voltage part. This one. Understand how you do the resistance of the rest of circuit. Voltage over to understand.
Oh, so you're unsure how I use nodal analysis. Is that what you're saying?
Yes, sir.
Oh, okay. All right. Yeah, Mr. Wilson. You had your hand up.
Yes, sir. I just wanted to know, what did we accomplish when we replaced most of the circuit with the 16.667? I understand how you got it, but I want to know why we did it. For the
What
circuit.
we're doing here, we're applying Thevenin's theorem in circuit analysis. And what the theorem says is that we can reduce that network to this. That's what the theorem is saying. So you get a complex network, you reduce it to a resistor in series with a source. Now, let us say, for example, instead of having just the 24, I had a variable resistor. Let's say that where the 24 is connected, it was a variable resistance. And it ranged from 40 to 100 ohms. Okay? Question. Which would make more sense? Would you include these different resistance values and calculate the current? Or would you prefer to find the Thevenin and then put in these various values? Which would make more sense to you?
Finding the Thevenin. So.
So you have just found the value of the Thevenin equivalent.
So I have a question. How did you come about the 24?
Hold on, Mr. Morgan. I'm still speaking to Mr. Wilson. Just hold on. Right, Mr. Wilson? All right, so it's about reducing complex networks into a simple network, which you can then use for various calculations.
So, sir, but the example you gave with the variable resistance. So we would do a similar thing to find the current if we were in a situation where we want to know the value of that resistance to get a certain current or something like that.
Well. I'm not sure I fully understand what you're asking, but it would be almost counterintuitive, right? If you already have the current to then go in the reverse for the resistance. A simple way of thinking, well, I shouldn't say a simple way, but the perfect application of Thevenin would be you buy a music system, for example, and where the speakers are to be connected, you'll actually see a resistance. They tell you what resistance speaker you should use. Yeah? What they're really telling you is that at that point, the Thevenin impedance is what you're seeing there. So it tells you that for best output, you use an 8 ohm speaker. Now, persons would, possibly see a 6 ohm speaker, and it is much larger than the 8 ohms that you have, and they would connect it because it's big. It should give you better sound. The truth is, however, that you get much better transference in terms of power with the perfectly matched speaker. But I'm trying my best not to step into other things or to deal with other things, which you'll have to do in your labs, right? In terms of a theorem that you will have to treat with. Yes, Ms. Onfra, you had your hand up. Pardon me?
I was saying, never mind.
All right, somebody else had shouted out, but yeah.
Yes, sir. I had one question about the 24 ohms. How do you get to that?
Get to the 24 ohms.
Right.
Oh, so you were late coming to the class, right?
No, not quite. I was here from the beginning of the question.
Oh, so you wrote down the question.
Right.
Pardon?
Yes, sir, I did.
Oh, well, I can't answer you then because there's nothing I could add. It's in the question.
Okay.
So,
Sir.
here we have a new circuit. So take this for me. This again is one that we have looked at. I believe we had solved it using nodal analysis. Yeah. So the question here is for us to find the current through the 8 ohm resistor. So what the current through the 8 ohm resistor? All right, now, I know I just use 2 nodes, but I want to stretch you a bit. Okay, so let's see now. So Williams, got it? What's the first step?
Select 2 nodes, sir.
Hmm?
B1 and B2, sir.
All right, look at the question. Look at the question.
Yes, sir.
What are you asked to do?
Determine the current through the 8 ohm resistor, sir. Redraw the circuit.
No, hold on. Is that the question? It's not that trick, Just look at what is before you. What are you asked to do?
Sir says use Thevenin theorem to determine the current flowing through the 8
Okay,
ohm
so that's different from what you said earlier. What you said is to just find the current through the 8 ohm. But you are asked to use Thevenin in finding the current. So now that you have determined that you must use Thevenin, I go back to my original question. What is the first step?
We would redraw the circuit without the 8 ohm, sir.
Thank you. You see, now that we have the question right, the steps kind of change.
Yes, sir.
So redrawing the circuit. Let's get the values. 2, 5, 13. All right. So based on the circuit before us, all right? Based on the circuit before us, still with you, Mr. Williams. Sorry if you thought you got nowhere. Huh? So,
Yes, sir.
pardon?
I'm here, sir. I'm here.
All right. Given the circuit, now that we have redrawn it, tell me which method you would want to use to complete the analysis. Totally up to you. Has nothing to do with me. What method would you want to use? You want to find the Thevenin voltage. That's the voltage at this point. If you go here, you can answer the circuit, Mr. Williams. All right. Mr. Williams is frozen. Let's see now. That's Sinclair. What you do? What method you want to use?
I was looking at it and wondering if mesh would be simpler.
Tell me why mesh would be simpler. What you want? You want the voltage across here, right?
Right.
Okay. So I would mesh be simpler.
I'm just looking at it. I haven't decided on that.
I want you to think it through. All right, help me with the reasoning. You're telling me that you're wondering whether or not mesh would be simpler, all right?
Right.
So let's work with you. Let us say I put in these mesh currents. And this is 1, that's 2. I don't want you to give me an answer. What I want you to do is to tell me what you would have to calculate in order to determine the voltage across that open circuited terminal. Port.
I'd have to calculate the voltage across the 2 ohm resistor and the voltage across the 2 amp source.
Now you answer me. How simple will that be?
Not as simple as using node.
All right. And you're actually making the point for me, Mr. Sinclair. Because many students, because they think that nodal is this or mesh is this, nice, simple thing. Their first instinct is to run to mesh. Yeah. But it is not just, what did I just do? It's not just about the mesh analysis. It is what do you do after finding the mesh currents. You with me?
Yeah.
So using mesh analysis for me would be an absolute no-no. It don't make practical sense. All right? Just going to make your life miserable. So now that I've kind of given away Obviously, I am expecting you to use nodal analysis, right?
Right.
Good. So since we have gotten over that first hurdle in terms of which method we use, tell me where you're gonna put your node.
Okay, I'm going to put my reference node at the junction between the 2 power source and the 3 ohm resistor.
You mean down here, sir?
Yes.
Oh, all right.
And I'm going to put V1 at the intersection of the 2 ohm and 5 ohm.
You up here, sir?
Yes.
Okay.
And then I'm going to put V2 at the junction between the 513 and 4 ohm.
All right. Now, I want you to tell me why it is that you chose to use V1 and V2. Is it because it is something that we have always done? Is it because I did it in the first question? Or did you look at this circuit and make a determination that that was the easiest thing?
Well, I look at that and I realize that seems easier for me.
Seems easier. Not a problem. Is anyone in the room of a different opinion to Mr. Sinclair in terms of using these 2 nodes? Apart from me, of course. Anybody want to join me? If you join me, I have to work it out. Everybody get cold feet now.
Sir, give us an idea, sir.
Huh? Idea?
Give us an idea, sir.
I give you an idea from last week, Monday. What do you think the teacher? Teacher know that. Eh? All right. And this student is just part of the reason why you're gonna have to practice, because it's only practice going to get you over the earth. All right? There's no other way, right? No other option. You're just gonna have to do the work. Now, I'm gonna just put one node here. Call it V1. Okay? Now, Mr. Sinclair, since nobody wanted to challenge you, and since I am now telling you we are going to use only one node, I want you to write for me the node equation at that node. Go ahead. At node 1. Go ahead.
At node 1. At node 1. So that would equals to the
remember, we're looking at the currents leaving.
Right.
Good. Your turn.
So we have two amps on this in entering. So we are going to have -2 amp over 7. No.
-2, but it's current we're looking at, you know, you have the current, 2 amp, right, so, where you're dividing.
Yeah, that's what I said. So it's -2 amp plus 3 amp what's it? I know the resistance.
Is that the only branch connected to the node?
No, so I'm saying now plus V1 over 7 ohm.
Is that equation right thing?
Yes, equals 0.
Equals 0. So that means V1 over 7 is equal to?
Equals to -1.
Which implies that V1 is equal to -1? -7 volts.
Right.
All right, so V1 equal -7. All right? We good?
Yes.
Good. Now, how would I now get the voltage at this point? I'm not gonna call it VA. Can I quickly calculate VA?
Sir, I was just
You know,
gonna
the current
ask if
Hold
you had
on,
enough
Mr.
current.
Wilson. I didn't acknowledge your hand. Hold on. Yes, Mr. Sinclair.
Right, so yes, you could calculate that, knowing that you know the current flowing through the 5 ohm resistor, you know the
Yes.
voltage at V1.
So what do I do?
So VA would be equals to,
Before we get to VA, what other information do I need? Since you said we know the current through the 5 ohm, what would
right,
I
so we need to determine the voltage drop across the 5 ohm resistor,
which is?
which now would be 2 times 5, which is 10.
10.
10 volts.
Now that I have the 10, what other information do I need? Apart from the value, what do I need to put in? I have the 10. What other information do I need?
Okay, you need see, VA plus.
Hold on, man.
10.
Before we get there, Mr. Sinclair, I have the 10. What else do I need before I move on? You just calculated 10. 2 times 5, 10.
10 volts. 10
But
volts.
what else do I need? In addition to the 10, what else do I need to indicate?
The direction, whether it's a voltage drop or a rise.
Okay, but how will I determine that?
Direction of current flow.
And how does that help me?
Well, if the current flow is leaving the positive end of a resistor,
Oh, no. It is the terminal that the current enters that we put as pulse.
right?
So therefore, you're going to put the plus here, so, and the minus here, so. It is what you got on the exam on Saturday. So I gave you the voltage, so you must know the direction in which the current is flowing. So the 2 amperes is heading that way. So you have plus minus. Now let us start at V1. I'm moving from V1 towards VA. Do I have a voltage drop or a voltage rise?
You have a voltage rise.
Okay, so I start at -7 and I've risen by 10. Where do I end up?
So you're at 3.
3. How many lines have we written down here?
3 lines.
3 lines. Now, when you looked at the circuit initially, it looked like you were gonna write 3 lines?
No.
Good. That's the value of practice. And that, as I said before, is what's gonna make the difference between someone finishing the paper in 1 hour and someone staying for the 2 hours and only do 1 question. That's the value of practice, or this is the value of practice. I hope I'm making myself clear. You know?
Yes, you are.
So now we know that VA is equal to 3 volts, which implies that E Thevenin is equal to 3 volts. We now redraw the circuit, and what's the what would be the internal impedance for the current sources? Mr. Allen, Richard Allen?
What is it, sir?
The internal impedance for the current sources would be, or is?
Comment.
What are you working on? There's nothing to think about, Mr. Allen. Anybody, what's the internal impedance of the current sources?
Open circuit, sir.
Infinity, so represent it with an open circuit. So if the sources have If the current sources have infinity, I'm now redrawing the circuit. We have here 5. So what's the Thevenin resistance? What is our Thevenin equal to?
12.
Pardon? What's our Thevenin?
0, sir.
So you're telling me if I put a ohm meter here, so I can get 0 ohms?
Sir, 12 ohms. 12, sir, 12.
So our Thevenin is 12 ohms. So the Thevenin equivalent (12 ohms, 12 volts, 3 volts.
Wait, there's 2 copy. I can write down, but this is a copy is a mouse. Copy is a mouse.
Boom.
I trust we are now clear as to why some persons remain in this module. All right. If that is their outlook, I am sure we will see them in 2025. Copying is a must. That's interesting. But we move on with those who understand the value of education. Let's move on. So 8 ohms would be equal to 3 over 12 plus 8, which gives us 150 milliamperes. And of course, if you go back to the circuit that we showed earlier, that we analyzed last Monday, just using straight nodal analysis, you would have found the current to be 150 milliamperes. So we obviously know that our approach is correct. Oh Lord, help us. Okay, so we're going to pick up the tempo now because a lot of what I've been doing since we started this evening is nodal analysis, looking back at what we have already completed, which means that, you know, many persons have not spent the time, as I instructed, to go over the material. So in a bit to force you to do it, I will not be spending the same amount of time going through the next set of examples. So the next theorem we're looking at tonight is Norton's theorem. And Norton says that any two-terminal network, you know, describing the same network as Thevenin, but in this case, he says that the network can be replaced by a single current source in parallel with a single resistance. So Thevenin talks about a single voltage source in series with a resistance. Norton says a single current source in parallel. So that's the only difference. Thevenin, voltage and series. Norton, current and parallel. All right? So we now define the current and the current source and the resistance. So the current, again, just referencing Thevenin and showing the link between the two. The current for your Norton equivalent is the short circuit current passing through, the current passing through the short circuited terminals. So where Norton talks about current flowing through short circuited terminals, Thevenin spoke about voltage at open circuited terminals. So if you understand Thevenin, Norton would be the antithesis of that. Okay? Thevenin, voltage series, open circuit voltage. Norton, current, parallel, short circuit current. The resistances are the same. So the Thevenin and the Norton resistances are the same in terms of definition. So I go back to the question that we just looked at in terms of applying Norton's theorem. So we're going to apply it to the same circuit. So this time we put in the short circuit. Now, I know I've been saying it, but you know, the truth is, there are many ways that we can look at this question. We can use mesh analysis, but remember, it is totally up to you. Totally up to you. So we put in the short circuit, and I am repeating the point that the method used is your prerogative, your choice. I'm going to use mesh analysis, even though, and you can do this in your own time just to build your confidence. I'm going to use mesh analysis, but we could have used nodal. And actually, if we use nodal, it would have been simpler than mesh. I'm just telling you that up front, all right? So if we are using mesh analysis, having redrawn our circuit, we put in our mesh currents. Where the bottom of my slides are being cut off. Anyway. So for those who are interested, you know, just to, as I said, confidence booster. If you were to use nodal, I would have simply put in a single node right here. Yes. Now, because you have the short circuit, it means that the current that passes through the 8 ohm would bypass that branch because that branch is now short circuited. So you'd have one equation, which is, if we call that node 1, it would be V1 over 8 plus V1 over 20, V1 plus 25 over 5, all right? And once you find V1, then you can easily find the current passing through the 8 ohm, which will be the current through the short circuit. But as I said, whoops, that's just for anyone who may have an interest. Okay, so we're using mesh analysis. Using mesh analysis, we form the mesh currents. I'm not going to go through the step-by-step formulation of these currents. Those are the 3 equations. And we solve them simultaneously, and we get the current to be 4.16667 amperes. All right. So having solved our equations for I1, we see that based on the circuit, I1 would be equal to I Norton. All right. And as I said before, R Norton, the resistance seen looking into those terminals. We see that it's the same circuit that we had as before. All right. So, which means that again, the impedance seen looking into the terminals would be equal to 4 ohms. All right, and I'm you know, at this stage, I'm assuming that you have done enough work with the resistance equation, so you can easily write the equation for this and solve. All right. So it means that your Norton equivalent would now be that current that we just calculated, the short circuit current, in parallel with the 4 ohm resistor. Okay, now the resistor that we had removed was the 24 ohm resistor. So I would reconnect that to my Norton equivalent and find the current through the 24 using current divider. So of course, I24 would be equal to I Norton times 4 over 28, okay? And like before, we get the 595.24, just confirming that, you know, our method is correct. Okay, now we have looked at the Norton equivalent, we have looked at the Thevenin equivalent, yes? Let's put them side by side. So we have the Norton on the left, the Thevenin on the right. It may not jump out at us immediately. However, what we see is that for the Norton equivalent, if I were to multiply 4.1667 by 4, I would get 16.667. All right? What that means is that I Norton is equal to E Thevenin divided by the Norton or the Thevenin resistance, which are one and the same. Yeah? So the Norton current is equal to the Thevenin voltage divided by the Thevenin resistance. question is, you know, if they're related, what's the real benefit of finding any one of them? Bottom line is, students, and I'm telling you this from now, so that you will not be surprised later on. The key points to note. The key points to note. One, what I just showed you is what you would have possibly done in physics, and they told you it was source conversion. That's one. Two, you're going to run into some circuits where you are required to use the Thevenin equivalent. Right? So I'm telling you that. You're required to use the Thevenin equivalent. However, calculating the Norton equivalent may be easier. So what you would do is to find the Norton and then convert that to the Thevenin, or vice versa. You may need to use the Norton, but finding the Thevenin is easier. So you'd find the Thevenin and convert it to the Norton. All right? Now, the third point that we're making here is that the resistance, that Thevenin resistance that we have been talking about, it's equal to the open circuit voltage divided by the short circuit current. All right? Now, the application for Norton and Thevenin that we have looked at so far, we included only independent sources. Now, we know the internal impedance of an independent source. We know that for a current source, the internal impedance is infinity. For an independent voltage, it is zero. So in finding the Thevenin resistance, we could easily replace these sources by their internal impedances. However, where there is a combination, please note, where there is a combination of independent and dependent sources, we have to rely on the relationship between the open circuit voltage and the short circuit current. So we'll have to find both. So if you have a circuit, it has only independent sources, you can use the application I just showed. However, once there is a combination of dependent and independent, you have to then find the open circuit voltage and the short circuit current. So let's take an example. All right, so there's our circuit. We want to determine the Thevenin equivalent at the load terminal. So it's at this port or those terminals. All right, so question is, how do I go about doing this? As before, I'm going to use nodal, and I want the open circuit voltage, I want the short circuit current. Yep. So we start by finding the short circuit current. And as I said last time, your choice of node or reference node is totally up to you. Which means that it's also totally up to me. So I'm choosing it at this point. Right? So I'm putting node 1 at this point, and I'm putting node 2 all the way down here. I'm putting my reference here, and I'm doing this to simplify my calculations. With the reference at this point, immediately I know that V1 is equal to 12. So it means that all I would need to calculate is V2. So I structure the question, I do my assignments to make my life easier. All right, now, using nodal analysis, I write my equation. V1 is 12, and then at node 2, we have 2 minus 1 over 3, 2 minus 1 over 6, 2 over 4, and 2Vx over 1. But of course, we look back at our circuit for Vx, all right? And Vx is the voltage across the 3K with the upper portion being positive. So you could have written it to say V1 minus Vx equal V2, all right? So you start at V1, you'll be subtracting Vx, and you end up at 2. Which is why we have V1 minus V2 is equal to Vx. So I make my substitution, and immediately we are able to find V2. The short circuit current is a current through the 6K, because that is the resistor between nodes 1 and 2. All right, so the short circuit current, as I said, would be the current flowing through the 6K. We have V1 minus V2. Over 6. So the short circuit current is 2 over 11 milliamperes. Now, when in finding the open circuit voltage, yes, and this is why it's important that you are comfortable with all the methods. You know, don't try and shy away or try and master mesh analysis because it will fail you, both figuratively and literally. All right. So in finding the open circuit voltage, note I basically have written back the same equation as before. However, now that I have open circuited this point, I just simply eliminate the 6K. So I still have V1 equal 12, but now I have V1, V2 minus V1 over 3, V2 over 4, yes, and minus 2 Vx over 1. And so V2 is found to be 336 over 31. I mean, if you want to use decimals, you know, be my guest. Okay, so the open circuit voltage is the difference between 1 and 2. So we get 36 over 31 volts. And so the Thevenin resistance is now the open circuit voltage over the short circuit current. And that's our answer. As I said, I have left them in fractions. It makes life easier. But if you choose to use decimals, then, you know, be my guest. All right, so your Thevenin equivalent and your Norton equivalent circuit would be as shown. So whatever the value for RL, you just put that in and you are on your way. All right, so what have we looked at? One, we have looked at the basic definitions in terms of Thevenin and Norton. Two, we have considered circuits that have independent sources only. And for those circuits, we can replace the sources by their internal impedances. However, with the inclusion of dependent sources, because we do not know the internal impedance for dependent sources, we now have to resort to the use of finding the short circuit current and the open circuit voltage in order to find the resistance, the circuit resistance. All right. So that's the penultimate variation. Finally, we now go to circuits that have only, oh, well, if you're interested, you can screenshot that. I'll talk about it another time, but we're running out of time tonight, so I will have to move on. All right. There's just one that I'm going to speak about, though. You see this one? It is something that many persons consider negative, but it's actually one of the most positive things that you can do for yourself. And I'm speaking now especially in relation to networks. Now let us say that your real challenge is, and I think somebody actually mentioned that some time ago, but anyway, let's say your challenge is with fractions. You have a problem just doing fractions. Recognize that as your limitation. The limitation may not necessarily be networks, but having formed your nodal equations, you just can't simplify them. Once you identify that as your weakness and focus on correcting that, then nodal no longer becomes a problem. But I'll tell you my own limitation and how I have learned to address it. My biggest limitation is that I cannot do productive work or meaningful work when it is daylight. So my most productive time, early morning and in the evening into night. All right? So when I need to concentrate, really concentrate, I have to get up at 3 or 2 and do the work. If I have to really focus, because I am accepted that during the day when everybody is around, you know, I'm in the office, I can't get serious cerebral work done. You need to think about where your strength lies, yes? And based on where your strength lies, I'm sure nobody is calling me in the office at this time, so I will drop that one. All right. You have to make sure you understand that, okay? And address it accordingly. So if you're a night person, structure your day so you do your most productive work at night. Okay? That's the only one I'm going to focus on. I move right along. If your circuit contains only dependent sources, it must be understood that the circuit cannot start by itself, because a dependent source, the voltage or current across or through a dependent source, is, as the word suggests, dependent on the current or voltage somewhere else in the circuit. So if I only have dependent sources, then there really is no possibility for any voltage or current anywhere else. And so we said that the circuit can't self-start. It means that the open circuit voltage, yes, and short circuit current would be equal to 0. However, we can still find the Thevenin resistance. So if we have a circuit with only dependent sources, we can still find the Thevenin resistance. How do we do that? Come, Mr. Sinclair, I know the day is long.
It is.
To determine this resistance, what do? One, we insert an independent voltage or current source at the terminals we have an interest in. And then we find the corresponding current or voltage. Let me explain that. So if I put in an independent voltage source, I'm going to find the corresponding current. And if I put in a current source, I'm going to find the corresponding voltage. So for a circuit with only a dependent source or dependent sources, I would connect an independent voltage or current source and find the corresponding current or voltage. All right? Sorry about that. All right, so how do we do that? All right, let me take this call. Apparently, let's see. My apology. Okay, so the application. Take the circuit, please. All right, so in terms of application, as we said, what we do is to attach a voltage or a current source. For this circuit, I'm going to attach a voltage source. Okay? So we redraw the circuit. It's the same circuit coming back. I now add the voltage source. All right, so here's my voltage source. And note, I am using a value that makes my life easy. Could have used 10. I mean, 10 is a nice round number, round clean number. All right. And based on the resistance values that I have here, you know, we either going to have 2 or, 5. In this case, it's 0.5. Yeah, but it doesn't really matter. Use a value you're comfortable with. 100 volts doesn't really matter. Okay. So we have our 1 volt source connected. The next step, remember, the objective is we put in a voltage source and find the corresponding current. Or we could have put in a current source and find the corresponding voltage. So I'm going to try and find the current, right, that would flow into the circuit. And this, technically speaking, students, is just like operating a voltmeter. We have already explained how a voltmeter works, yeah? It has a source, you connect it, depending on the current that flows, then you get a resistance reading. But that's a voltmeter, ohm meter, yeah? All right, so let's go. Writing Kirchhoff's voltage law, at node 1, we'd have V1 over 1K plus, minus, plus, minus, equals 0. Vx from the circuit is equal to V2 minus V1. And so simplifying, we get 2V1 plus V1 minus 2V2 plus 2V1 plus 2V1 minus 2V2 equals 0. Or 7V1 is equal to 4V2, or V1 is equal to 4 over 7 V2. Bearing in mind that we were the ones who inserted V2, so V2, of course, is 1 volt. All right, we have that. So I go back to my circuit. I remember what we're trying to find. In this instance, it will be the current IY. So I'm finding current IY. And IY would just be the sum of I1, 2, and 3. So it's those 3 currents that we're looking at. So I1 would be V1, or sorry, V2 minus V1 over 1K. I2 would be V2 minus 2Vx. Yes, over 2K, and I3 would be V2 over 2K. And here they are. So for, in this instance, we have VIY to be equal to 1 milliampere. And remember what we're finding is our Thevenin, which is equal to V open circuit, V short circuit. Our voltage was 1 volt, and we have 1 milliampere, so it means that this is 1K. So our Thevenin would be 1K.
So should it be V short circuit or I short circuit.
I'm feeling that, Mr. Sinclair. All right. All right, so our Thevenin is 1K. All right, so, you know, that's it. We've looked at Norton, we have looked at Thevenin. What I would encourage you to do is all the circuits that we have looked at, and this is a study method I used when I was a student. I don't know if it will help you, but I'm gonna tell you anyway. You see, in those circuits that we have looked at for the last 4 weeks, I would take each of those circuits and I would use all the methods that we have looked at and work that one circuit. So all the examples I gave you, you know, whether it was a mesh analysis or a nodal, if I gave it some examples in mesh, do them over in node. Do them over again using Thevenin or Norton, just to build your confidence. And so I had wads of paper with one question done 5 different ways. So it means that all the methods became, you know, routine to me. All right. While we wrap up, we have a few minutes left. I'm gonna ask you to attempt this question. While you do that, I will